The first step to drawing valid resonance structures is understanding a set of rules that we cannot break. First, all structures have to have the same number of total valence electrons, and that ultimately means that we're not adding lone pairs or adding bonds that didn't exist in the first structure or atoms. The second one's a little bit easier to understand. We can't exceed a valence of electrons. So if we look at, for example, the two structures of acetate or the two structures of nitrate, all the atoms have 8 electrons, and we're not exceeding them. We don't have 10 electrons around any of those atoms. We also don't move atoms. So in all these structures, the atoms are in the same place. The only thing that's done is that we've taken lone pairs of electrons, or those that are involved in the pi bonds, and we've showed a reallocation of them, or a sharing of them. In our first structure, we have a lone pair on the oxygen, a third lone pair that we've shown now in the pi bond, and then we've also shown this pi bond being reallocated to a lone pair of electrons. Our last rule says each structure has to have the same molecular charge. And if we look here, acetate has a net charge of -1 and -1, and nitrate is -1, and this structure of nitrate is -1 as well. The next set of rules is going to help us identify, if we have more than one resonance structure, which one represents the best Lewis structure. For the examples that are on the bottom of this page, you might be able to determine that the two structures of acetate contribute equivalently to the real structure of acetate, or the two structures of nitrate both represent the structure equally, or both of the oxygens share the charge. But that's not always going to be true. Take, for example, the structures on the bottom. In one case, we have a positive charge on a carbon, and in another case, we have a positive charge on an oxygen. You can probably tell that these look a lot different from our prior examples, and indeed, the oxygen and carbon don't share the positive charge equally. And we use these rules that are here to help us decide which structure is more preferred. They're listed in order of their importance, and so if we can determine which resonance structure is better by only the first or second preference, then we don't need to look any further. That's true in this example. Between these two molecules that are drawn, we can see that only the structure on the right has all atoms with full valencies. Notice this carbon has just 6 electrons around it, whereas this molecule, all atoms have a full octet. And so that means that that's the preferred structure. We can move on and go down the list for practice here. We can see the structure on the right also has a maximum number of covalent bonds. We don't have more than one charge, so preference number 3 doesn't really hold. And nor does preference 4 because we don't have a negative charge. Let's look at some other examples. The molecule that's in the center here is known as an amide, and I've drawn 4 additional structures surrounding it that may represent valid resonance structures. Your job is to determine which of them are relevant, and then of those that are, what type of priority do we see with them? Are others more stable than others, or represent more valid structures? You might want to actually pause the video and take a look and see if you can find, do any of the structures represent invalid resonance structures? If you said that this structure was invalid, you are correct. It turns out that the nitrogen there has 10 valence electrons around it. Can't have that. For the remaining structures that are here, we want to use our relative importance of resonance contributing structures to help determine which ones are the best here. The first preference says we want a molecule that has atoms that have filled valence shells. And I can identify that this oxygen doesn't have a full octet, this carbon doesn't have a full octet. This molecule, we see that all atoms are filled valencies, and this molecule also. So these are probably going to represent my best resonance structures. Let's move to the second rule. We want to have a molecule that has a maximum number of covalent bonds. Well, here we've got a pi bond, and here's a pi bond. And in the other two structures, which we've already said aren't very good, we're lacking that extra bond. So again, these are probably my better structures. The third preference says we want the least separation of charge. Now, another way to say that is you want to have a molecule with no atomic charges. That basically says you have no separation of charge. So it looks like the center structure here is indeed our best Lewis structure, and the one on the right side represents maybe our second best structure. Between the other two molecules, we want to move on to the fourth preference in our list of relative importance, and we can see that it is better to have a negative charge on the more electronegative atom, and that represents the leftmost structure. So this will then be our third best structure. And the top structure doesn't really have much going on at all for it, and just is not relevant. Benzene probably represents one of the better examples to highlight the theory of resonance. Here I have a structure of benzene drawn, and on this left side is the electronic structure of benzene, and you can see the electron density is symmetrically shared right in the center of the molecule. So the structure on the right side doesn't do a really good job of highlighting the electronic structure. It doesn't show a lot of electron density on the left side and not very much electron density where the sigma bond is, and then more electron density here and then less here and more here, but instead it shows it symmetrically centered around the middle of the benzene molecule. You may have actually seen benzene drawn another way, maybe like this, where the double bonds are in different positions. And that's equivalently correct. In fact, we can say these two are resonance hybrids of each other, and we can draw these curved arrows that you saw before to show how those pi electrons can be shared in another position. Maybe you've even seen benzene represented with a circle in the middle. And that's common to highlight the fact that the pi electrons are equivalently shared within the center of the molecule. The molecule on the right side is known as benzaldehyde, and when we compare the two electronic structures, you'll notice that there is a high amount of electron density up towards the oxygen here of the carbonyl for benzaldehyde. But note, more importantly, the center of the benzene ring for benzaldehyde doesn't have a whole lot of electron density there. So the red region for benzene represents high electron density. We've kind of lost that in benzaldehyde. Well, we can use resonance theory to actually show us how that happens. I know that oxygen is electronegative, and there's a natural tendency to share electrons towards electronegative atoms. And so one of the logical arrows I can draw will be from the pi bond up to the oxygen. And that's going to give me a resonance structure that has a negative charge on oxygen and a positive charge on carbon. So we have 3 lone pairs up top, and there's a plus charge. Now this is fine, but it still doesn't really show why the center of the benzene ring lacks electron density, until we show now more arrows which show that these electrons are being shared towards that positive charge, and we now make a pi bond on the outside of the ring. And so that structure is going to show a positive charge in that position. Here's our new pi bond, and we have an O minus, and there's those 3 lone pairs. We can now draw more resonance structures showing this pi bond moving here, or rather being shared in the position to satisfy the positive charge, but we create another one, another positive charge. So there's the positive charge. I'm running out of room on the screen here. I'll have to squeeze one in really small, but if I take this pi bond and do that, then I get to one last structure. Where am I going to put this? I guess I'll squeeze it right here. We have a plus charge here, and this is no different than before. So remember what resonance structures are. They represent the molecule that we're considering. We're representing the electronic structure of benzaldehyde here. And so all 5 of these structures lumped together into one is what can be best used to rationalize the electronic structure of benzaldehyde. Now, if you wanted to determine which one of these is most relevant, it's the very first one right here. And so when we're asked about drawing the Lewis structure of benzaldehyde, that's the one we give. But it's sure nice to know that the role of this carbonyl on the outside of the ring is actually to remove electron density out of the ring. And that explains the electronic structure of benzaldehyde. Let's practice determining which Lewis structure is best. You'll use your relative importance of resonance contributing structures to determine that. The first thing says we want to have all atoms have a filled valence shell. Well, right away, I think I've come to an answer. This one's got all the full valence shells. We don't need to consider any of the other preferences. In this pair of structures, both molecules have all atoms containing full valence shells. So now we have to go to the second preference. We want to have the maximum number of covalent bonds. Well, there's no difference there again. Least separation of charge. Well, we don't have a plus and a minus. So now I'm down to my last rule. We want to have the negative charge in the more electronegative atom. And there you go. Looks like I found a winner. That's our preferred structure. This first example is kind of a silly one, and I put it there on purpose. When you have molecules that are just made up of carbons and hydrogens, there's really not a lot of reason to consider reallocation of electrons. Most of the time, you'll find that molecules have oxygens, nitrogens, or more electronegative atoms, or maybe there'll be charges that are there as well. And those are going to highlight some unique aspects of the molecule that may actually then have some relevant resonance structures. So this first molecule, I'm not going to draw anything for it. There's really nothing special going on here. In our second example, however, now we have an electronegative atom there, which can be pulling electrons towards itself. So it wouldn't be unusual to suggest that some of the electrons can be shared up towards that oxygen. That gives me a new structure that looks like this. We have 3 lone pairs now and a minus charge, plus charge here. And then I can draw another curved arrow from this pi bond over here. That's going to draw a new pi bond. And we'll have this structure, the negative charge, like that. Can you identify which one's the best resonance structure of these 3? Well, it's the one over here. It doesn't have any atomic charges. All filled valencies, maximum number of covalent bonds. Between the other 2 structures, which one do you like better? I'd say this one here. This is our second best structure because we have the least separation of charge. Let's try this again with a couple of other examples. I have a positive charge on the first example here, and positive charges generally attract electrons. So it wouldn't be unusual to suggest that these pi electrons can be shared over here to satisfy the charge on that carbon. Although, ironically, what we end up doing is just creating another carbon charge. So we'd have a double bond here, we'd have a plus charge in that position under the nitrogen, and we'd have this. And I'm going to end up using this lone pair on the nitrogen, so I'm going to draw it in there, make sure you know it's there. And then the next thing I could do is show this lone pair being shared to form a pi bond between the nitrogen and the carbon. And I ran out of room again, so that structure is going to look like this. Put a plus charge on the nitrogen. So amongst those 3 in the top example, which one do you think is the best structure there? It's that one, because we have all valencies filled. Let's move to the last structure here. We can show these electrons being shared down here towards the positive charge. That's going to give me a plus charge under the oxygen. Double bond will be there. And I can show a lone pair of electrons on the oxygen being shared here. And that's going to form a pi bond between the oxygen and the carbon. Looks like this. And which structure you like best? For the same reason, all valencies are full.